Let's look at an application of a rational function. And that we're going to talk about sound waves. Sound waves are interesting because they're a lot bigger than you might imagine. The frequency of a sound actually varies inversely with its wavelength. In other words, a lower frequency sound is a longer wavelength. And that kind of makes sense if you talk about a sound wave that kind of goes up and down like this. Sorry, pardon my choppy handwriting here. That's more of a lower frequency sound than a sound wave that goes like this. Again, horrible handwriting, but I hope you can get the idea. So a shorter wavelength, a distance from here to back in the same position on the next wavelength here, or from here to here, compared to the wavelength from here to here, or from here to here, a shorter wavelength represents a higher frequency sound, and a longer wavelength represents a lower frequency sound. So if you have a sound that has a wavelength of 34 meters, as in 100 feet, or twice the length of an ordinary house, that is a frequency of 10 hertz. Now that's a very low note, lower than most stereos can play, but there are some that can play them that low. Realize that we're talking about extraordinarily large waves here. Now what we're looking at here, the question is, what frequency does a sound signal of 120 meters, or 360 feet? What frequency is a wavelength that long? Well, if the wavelength varies inversely with the frequency, then what we're saying is that the frequency is equal to whatever our constant of proportionality is, divided by the wavelength. So it looks a little like this. So all we need to do is take our information we have to figure our constant of proportionality. We'll plug the frequency we know, which is 10 hertz. 10 is equal to whatever the constant we don't know is yet, divided by the wavelength we know, 34 meters. So that should give us be able to give us to solve for k so that we know what our constant of proportionality is with a sound wave. If we multiply both sides by 34, we get k is equal to 340. So now we have a k value, a constant of proportionality. We have another wavelength we're supposed to deal with, but we don't know the frequency yet. So what we'll do is leave frequency f as a variable, and we'll put in the constant of proportionality that we know now, 340, divided by 120. Well, 340 divided by 120 is about 2.83 or so. So that frequency then, if the wavelength is 120 meters long, or 360 feet long, then that's about a 3 hertz note. It's an incredibly low note. You can't hear it that low, but you'd probably feel it if it was high enough power.